They asked me to come and talk a bit about applications of portable XRF in the industry. So I just want to start with a big disclaimer. That is an image of my brain, done with X-rays, so it ties together. So I'm not an expert on the XRF. There's a lot of good resources out there if you want to know more. What I am is an Xplo geologist, and I've used this enthusiastically and sporadically for a few years now. So I'm going to just focus on applications and hopefully stimulate some thought about that for the audience here and not focus too much on the hard science behind it. So in that interest, I'll just do a one-slider on sort of the theory for those who are a little bit rusty or unfamiliar. Basically, you have an X-ray source in a hopefully handheld unit. X-ray source is stimulated, produces a beam. It's about 10 millimeters, can be collimated to 3 if you'd like. Produces a beam that interacts with the sample media, energizes electrons within the atoms that you're stimulating, ejects those electrons, and then outer shell electrons bounce back down to fill in those gaps, and in the process fluoresce or release a quantized amount of energy in the form of photons, which are registered by the unit, and then that produces the data needed to interpret with the onboard software what elements and how much of each element is in that sample that you're analyzing. So that's sort of it in a nutshell. And then a little blurb, so this is, I guess it's old news for some people, the XRF, but maybe it's new news for others, but it's come a long ways. It's always improving. I don't think yet we're at the stage where it's a replacement for LabChem, but it can be a good tool if you want to make a quick decision in the field, save some money on a drill program, for instance. You can get some hard data to support your decision really quickly. And then also kind of, this was touched on this morning, but it's maybe something worth reinforcing, that integration of data it's key, I think, and this is no different. So it's useful when you combine it with your logs and your ASD results or your MagSAS or whatever else you can get in a rapid time frame. So you can make some of these decisions in an informed way without having to wait for laboratory chemistry to arrive. So I'm with FQM, as mentioned in my bio. So First Quantum's been using these sorts of apparatus for a few years now. So I'm just going to kind of flip through a few really quick snapshots of what we've been doing and where we're sort of heading towards with it. Sort of said that. Okay, so this is anecdotal more than anything, but going way back before I even joined the company, I learned this around the water cooler, but the first real broad use of it in First Quantum was in the Congo about 10 or 15 years ago, and there was a moratorium on shipping earth materials outside of the country for fear that a company would be robbing, something of value. So that applied to soil samples and assay samples. So there's no analysis possible outside of the Congo. Basically what the guys did was they took a bunch of soil samples on a grid over a big chunk of the copper belt and were able to analyze it with an XRF at the time and get some good quality data to target with. This isn't data from that. This project is no longer First Quantum's. It's a long, sordid story, but anyways, this is from a similar program in Zambia, and what is shown here is just a comparison done after the fact between the XRF results and the commercial lab results for copper. You can see the correlation is really nice. So it was useful for them in this other program to target their sampling and maximize their efforts. This is done, that's really hard to see. This was done on a magmatic sulfide deposit in Finland a few years ago by another team within the company. They found that the historic data from the mine was really focused on metals, and they didn't have much to work with for lithogeochemistry or alteration and things like that. So what they did, they went and did a pilot and analyzed a bunch of samples with the XRF and cross-checked them with up-to-date lab analyses and found some pretty good correlation. And we're actually able to do lithogeochem on an entire deposit for a fraction of the cost of reanalyzing all those samples. This was done on pulps from Drillcore at Kevitsa in Finland. This is another interesting one. This was sort of mineral chemistry study that we did in Panama a few years ago. So we were relogging core in Panama and found that there's zeolite minerals all through it. It's a large porphyry deposit, and we discovered that there's these low temperature minerals called zeolites. They're all over the place, and we were curious about whether or not we could use the chemistry of those zeolites as a vectoring method if they were concentrating pathfinders somehow. And if we could do that in a feasible way with an XRF. So really patient junior geo went through and hand-picked zeolite samples out of 2 pseudo-sections through one of the deposits there called Botica, and concentrated it up about 20 grams per spot. We analyzed those with an XRF a few times and then sent the material in for lab chem, and found that the results were really convincing. They were getting good. This is an example of stoichiometry, but the aluminum versus silica was plotted really nicely on the chabazite line. And I can't show the results, but I can say that yes, we were able to find some sort of zonation patterns and trace elements related to its distribution around the porphyry. So that was interesting. The less interesting part of that is that the footprint wasn't any larger than any other conventional technique that we come across, so there was no point in carrying it forward, but as a case study, it was a good learner. And then this is something that's more recent from First Quantum. We've been experimenting with, or trialing, I guess would be the appropriate word. We've been trying to move towards more systematic usage as opposed to these sort of pilots and mineral chem examples and things like that. So the group in Australia last year in Perth, they did a run of testing with the Vanta, and a setup really similar to this one in the corner, and came up with good results. So it's quite feasible using this. They're able to homogenize the samples quickly, pelletize them with a press, and then get results into the hub and back down really fast. So we're taking this philosophy forward and doing more of this type of work in active programs now through this year. So here's a couple of use cases from a prior employer. Active drill program usage and some data acquisition from historic cores. This is a mixture of RC and diamond drilling that we were doing on an active program. So we were getting results day of or day after drilling. These plots are just comparing those results against later to arrive lab chem to verify. It's really hard to see, I guess, but yeah, there's a 1-to-1 line there, if you can make that out. You can see the dispersion is a little bit looser than what we'd see with soil geochemistry, and the reason for that is that you're comparing point data from the DDH to homogenized interval data from the lab. But in any case, we found that the results were useful. We were able to do a few things with it. This is an example. This is sort of the type of thing that we're doing on a daily basis with XRF results. So we get these results back from yesterday's drilling, endeavor to put together some breaks in what might be lithology or alteration, send it back to the guys at the rig or compare it to their logs, and then fine-tune our picks on things like alteration and lithology. And in this case, it was actually quite useful because we're in a terrain that was heavily acid altered. So we're looking for porphyries in an epithermal district. There's lots of acid alteration that sort of makes things texturally hard to see, destroys a lot of mafic minerals. You end up with rock that's really white and full of sericite and quartz and things like that. But with the XRF, we were able to pick out some differences in trace elements, immobile trace elements that were really useful for logging purposes, and then later making a model. A little side note on that, this is something else I found, just another anecdote, I guess. It's story time, but a really nice thing about the XRF that I found over the years is that when we're using commercial analyses, we're using an acid digest of some kind, and things like zircon, as many of you have probably found, don't necessarily digest very well, and sometimes you can actually get a superior result from XRF for an element that's hosted in a refractory phase like that, like zircon. So something to keep in mind. This is another scenario that I'm sure many people have walked into. This nightmare scenario where you've got a lot of historic drill core. It's full of information. You might have some old historic logs with a couple of elements in them, but you want to do something more with that, maybe some lithology or alteration. But this was a case we came across a few years ago. And we got these historic logs. There were 7 elements in it, just metals. Not much you can do for corroborating the lithology logs and alteration logs, which we also had at the time. But because we had access to the core, we were able to send in a team, and they took a point reading every meter down the core And then we could compare that to the lab data and come up with our own sort of interpretations beyond that. So just to validate that, we checked the metals that we had in historic data versus metals in the XRF. We got a difference here. You can see the top two are copper and arsenic in the historic assays, the lab results, and the bottom two in the XRF results. So quantitatively, they're very different. We're comparing interval data to point data, so you can expect that. And it's a bit messier, but for our purposes at the time, just vectoring to more ore, we were happy because trends were largely the same. So this was sort of a good result for us and gave us the confidence to move forward and look at other things. So here's another example from the same project. This is just a few immobile elements. That's zircon, yttrium, and titanium plotted up in hourglass. And then I've put the historic strip log below it. So a few things jump out right away. Obviously, the dacite porphyry's got a very different composition than the surrounding rocks. So from there, we can go and start looking at other things. This is potassium over titanium on the right as an indication of how much maybe sericite has been introduced to the system. So we checked that and found that yes, there's a really nice trend of increasing potassium downhole. Verified what we see in the logs. We're happy now with the logging that was done historically, because they've logged an increased abundance of sericite downhole. And then we can start looking at a few things like pathfinder elements and drawing some conclusions about the genesis of this hydrothermal system. So you can see that the copper has affected the dacite porphyry, but arsenic and moly hasn't. So we've got a sense of timing on these sort of ore-related events all of a sudden. I just want to kind of sum up a few things I think that are important. So the guy's had too many x-rays, but some strengths, in my opinion, over the years of use. So the obvious one is the speed of analysis. You can make a rapid decision. You've got some hard data behind you. It's easy to use. It's portable. The leach strength issue I mentioned regarding zircon, this is a good one to keep in mind. Cost is low beyond the upfront. You can recover data in situations where you might not be able to do that otherwise. Another one is RC spools. We come across these in the desert all the time. People leave their RC bags out in the desert, the bags rot, and you've got little piles of RC. So we don't know anything about those cores other than it's there in this location and roughly how deep, but we can go back and analyze those piles with an XRF and do something with the chemistry data. Complementary techniques, so use it with your other data sets. I think that's hopefully clear. And yeah, I guess there's situations where you can do some mineral chemistry depending on the grain size and the homogeneity of your target phase and the elements you're looking at. Yeah, so weaknesses, it's semi-quantitative. You can take it to nearly quantitative. You have to do a bit of extra stuff with that. Put in matrix matched standards and correction factors. You have to strive for homogenized sample. You can end up with erroneous results from interferences. There's some poor implementation practices. You don't want to analyze a wet sample, for instance. There's more that can be done with this stuff. I guess this is more of a weakness on the user's part than it is on the machine. I don't know how many times I've been sitting in a meeting and somebody just wants to look at copper numbers and that's it, but you can actually do much, much more. And I'm sure that's not quite understood everywhere yet. The upfront cost can be a bit high. Certification, and sometimes the requirement, Chile, we have to certify everybody use it. I'm not sure about here. And then a little sort of cautionary tale. This is an excerpt from a press release from a junior in the early 2000s. And it was drilling ultramafics at the time and taking systematic XRF readings down the core and getting some tremendous nickel and chrome numbers, 0.26 nickel and 0.22% chrome. These big intercepts, really exciting stuff until you look at the core and realize there's no sulfides in it. It was all trapped in olivine and serpentine silicates. So it's not metallurgically accessible, but this junior is doing sort of a shifty thing and putting it out there for investors to look at, saying that they're getting these good intercepts. So you got to be cautious. They did have some fine print somewhere that said it was handheld XRF data, but anyways, things to be aware of. And a few other things to keep in mind. So homogeneity and presentation of the sample, this is something that's important in terms of accuracy and precision of your results, but it's an inverse correlation between that homogeneity and the amount of time required to get those results. So if you're happy with something that's a bit nuggety, you can take point readings, you can have results on your Drillcore that day, but if you need something that's a little bit better quality, you're going to need to split that sample, homogenize it, use something like that, for instance, and end up with a better result. So this takes time. It depends on what you're trying to achieve, I guess. Yet distribution of elements has an effect on homogeneity as well, so you get more nuggety results with alteration elements than you do with litho elements. And I'd really strongly recommend doing a baseline for whatever your application might be. You want to understand which elements are going to perform well and which won't before you get going, and get a handle on how much and what type of QAQC you need to implement for that. So anyways, there's, like I said before, there's lots of resources out there if you're interested in it. There's some good authors that write a lot about these portable XRF techniques. There's Michael Gaisley, Bench, Fisher, Cleverly, very good. Just Google them up, and it's good stuff out there.